For the Kinetics Lab, you will need to evaluate the energy for 3 different carbocation intermediates. That is, the 3 positions where deuteration can occur on 5-methoxyindan. If you look at the structure of this compound, you see that there are 3 hydrogens here connected at the ring at carbon 4, 6, and 7 that are each susceptible to electrophilic aromatic substitution. The structure of the compound is shown here as a line drawing with double bonds. When we make this into a carbocation, it will be an overall positive 1 charge species with multiplicity singlet. If we want to see what that looks like in a line structure, that would produce a formal charge at one of the carbons, and one of the double bonds would be removed, and we see 2 hydrogens at the position that we're considering here at carbon 7. Note that this is simply a rendering on a line structure that localizes the positive charge here. That's not what it is in reality. It's just resonance theory's way of presenting what the electrons are doing. The true molecule would have charges delocalized throughout the entire structure. So make sure that you do have 10 carbons, 13 hydrogens, and 1 oxygen, and that the overall charge is +1. That's the carbocation that we want to calculate. Notice also that it wasn't necessary to use a deuterium atom. We'll just simulate that with a hydrogen atom. We won't worry about the extra neutron that's in the nucleus because it doesn't affect the electronic energy all that significantly. Let's see how we would build this in GaussView. So if we go and start with a benzene ring, and we can add the aliphatic 5-membered ring by just adding methyl groups, and then we'll have to delete 2 atoms and connect up the 2 carbons with a single bond, and we can clean that structure and take a look at what we have. I noticed that the carbon that we connected from the 5-membered ring, the hydrogens appear to be not at a tetrahedral angle. There's a quick way to fix that. If any of your hydrogens don't seem to appear in a normal position, what we can do is we can delete them, and then using the add valence tool, the one with the hydrogen here, add them back. And when it adds them back, it does so appropriately so that we have a tetrahedral arrangement there. Okay, that takes care of that part. Let's add now the methoxy. I'll need to put an oxygen at this position and then finish by putting a methyl on the end. Okay, so this is our reactant. This isn't what we want to calculate, though. We want the carbocation intermediate, so we have to pick one of the positions. I'll pick position 7 for the moment. If I want to consider the electrophilic aromatic substitution at position 7, I can simulate that by simply adding a hydrogen at position 7. So I'll choose the add valence and click 1 time on that carbon. Notice now we've got 2 hydrogens attached there. If we look at the stoichiometry as reported, I have 10 carbons, 13 hydrogens, and 1 oxygen. That's as it should be. And when I launch the job, I want to specify that I'm doing an opt-freak, but that the charge is +1, spin, singlet, multiplicity 1, charge 1. That's how I would set it up, and that's how I would calculate the carbocation intermediate. The other 2 intermediates that you need are the same thing. You just put the hydrogen at the two other positions on the ring, and you'll be able to evaluate the three carbocations to see which one is more stable, and therefore the one that would indicate would be the faster position as far as the reaction is concerned. You see there's no need to put double bonds or charges here. We're specifying the overall charge as +1, and Gaussian will optimize the atoms and put them in the appropriate positions. If a couple of these are closer together than others, as was implied by the line structure, then that's fine, but we don't need to specify that when we're drawing in the molecule as input. Hope this was helpful. Have fun calculating carbocation intermediates.